We turn now to the subject of power series. Power series is a little different from the type of series that we've been encountering, and let me just try to explain very simply why. In the series that we've been encountering, there has been no variable. Some of you look at it and you say, well, what do you mean? Of course there's a variable, there's n. But n isn't really a variable. N is an index. The thing about the index n is the index is really just something we put in for convenience. In other words, if I write the sum from n equals 1 to infinity of 1 over n, we understand that this means 1 plus 1 half plus 1 third plus 1 fourth plus etc. So this is kind of a shorthand where I use the index variable and put it into the sigma. I could explain what I meant without an n. The point is that once I determine what the definition of the series is, the terms of the series are fixed. They don't change. Yes, they change from term to term, but the entire series consists of this term and this term and this term and this term. What we're doing with a power series is we're introducing a variable into the series. We're sort of defining a general series into which we can insert another value that we're calling x. Let me show you what that looks like. So we say that a power series with a center of C, and I'll explain, well, it'll become clear what the center actually is. A power series with a center of C is an infinite series of this form. It's the form that looks like that. So it's f of x, that's where the x comes in, is equal to the sum from n equals 0 to infinity of an x minus c to the n. So what that looks like is every term in the series has some term in an underlying sequence, which may be a very simple sequence. It could be a constant sequence 1, but it's going to have some term in a sequence multiplied by ascending powers of x minus c. So here we have a1 x minus c. I could write that as to the 1. I didn't put in the 1 because it's redundant. Here we have a2 x minus c to the 2, and then of course here we have a0. You don't see it, but we have x minus c to the 0 because anything to the 0 is 1, so we just customarily don't write it. And by the way, power series, we typically start them at 0. Sometimes you'll see us start with an index of 1, but the understanding of a power series is that it starts at term 0. If we started at a higher term, what that really just means is that the terms for powers, if I started at, let's say, at 1, what that would mean is that I'm assuming that the terms for the power 0 are just zeros and don't get written. So the general understanding of a power series, it starts at an index of 0. Now, a more common case of a series, this is the really general form of a series that I've written up here. Typically, we're dealing with series where the center is 0. Not always, but we might be. We often are. And if the center is 0, then we just write the series like this. We don't need to write x minus c because it would just be x minus 0, which is x. So those series look like a0 plus a1x plus a2x squared plus a3x cubed, like that. So here are just some examples that I've put up. So here's an example. F of x is equal to 1 plus x squared plus x cubed, which we can write as the sum from n equals 0 to infinity of x to the n. Now that's just a compact way of writing that it's all the ascending powers of x. And of course here you see 1, you say where's the x? That's just x to the 0. So this is an example of a power series with center 0. Notice, by the way, that I've said that there's always sort of implicitly at least this sequence a0, a1, a2, a3, but I mentioned it could be a very simple sequence. This is an example of that where every term in the sequence is just 1, so you don't even see it. That's why it's not written here. Here's a little bit more of a complicated example. G of x, which I've written as 1, plus 2 times x to the 5th, plus 3 times x to the x, sorry, 2 times x minus 5, 3 times x minus 5 squared, 4 times x minus 5 cubed. I should put in here, by the way, this is plus dot dot dot. If I didn't put it in the earlier one, yeah, I did. There's always dot 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 because these series always are presumed to go on forever. So this is the compact form of this series, which, by the way, has a center not of 0 but of 5. Get the color right. This is a series with a center of 5. See how it looks like this. The center is always, we always write x minus the center there. So this is a series with a center of 5, and its compact form is the sum from n equals 0 to infinity of n plus 1 times x minus 5 to the n. And you can see that that's true, that this is the n equals 0 term. So I have here 0 plus 1 is 1 times x minus 5 to the 0. Here, this is the n equals 1 term, this is the n equals 2 term, this is the n equals 3 term, and just verify, let's say with n equals 2, you can see that I have n plus 1, so that's 2 plus 1 gives me the 3 out there, and then I have x minus 5 to the n, so that gives me x minus 5 to the 2. So that in fact works, and here of course what we have is that an is the sequence n plus 1. Just write it in here. This is the an term in the power series. Okay, so the question is, what is different about the study of power series as compared with what we've been doing? And this is really the answer. Until now, what we've been studying really is the question of whether a particular series converges. We talked about comparison tests, the integral tests. These are things that tell us whether a series converges. We then defined these sort of companion series in the subject of absolute convergence. We defined the notion of a positive term series that we form by taking the absolute value of every term, which gave rise to the concept of absolute or conditional convergence, where we were making conclusions about whether a particular series or its companion series or both converged. But the focus has always just been on, does a particular series converge or does it not? Now, the thing about a power series is every power series converges somewhere. The question now shifts not to whether the series converges, but where it converges. That's going to be the central question that we'll be asking for much of this section, is where does a power series converge? And when I say where, what I mean is for what values of x can we plug in and get a convergent series? As you've seen, let's just take a look at this very simple series. F of x equals 1 plus x squared plus x cubed, etc. There are some values of x that I can plug in that are going to give a convergent series. There are some that would give a divergent series. That's going to be the question, is which values of x those are. And by the way, you can see in this case, at least, you may be able to see which other values it converges for, but you can at least see why it is that every series like this has to converge somewhere. Look what happens when I plug in the center 0. Then I just get 1 plus 0 plus 0 plus 0 plus 0 plus 0, so the whole series just equals 1. That's going to be the case for any series centered at 0, because I always am going to have just this term a0 and then plus a bunch of things that are multiplied by x. So if I plug in 0, all the other stuff disappears and the whole series just converges to its value a0, to its first value a0. That's why all series converge at the center. And you can see up here, I could do the same thing. I could plug in, if I plug in c, then all of the x minus c terms just become c minus c, or 0. So every power series is going to converge at its center at least, but the more interesting ones will converge someplace else. So that's what our study now shifts to, is where does a particular power series converge? This is how we investigate the question. This is the framework in which we investigate the question of whether a power series, of where a power series converges. So a power series has a concept called a radius of convergence. And I'll explain in a minute what that means graphically. So we've already discussed the fact that the power series has a center. So the radius of convergence really tells us how far from the center the convergence extends. So what that means is that the location of convergence, or what we usually call the interval of convergence of a power series, always looks like this. It has its center at the middle, and it extends for a distance r, the radius, in either direction, or in both directions, really. So for the most common type of case where the center is 0, what that means is that the radius of convergence extends from negative r up to positive r. By the way, just as an aside, you might wonder why I'm using this term radius. Isn't that a concept that's associated with circles? To understand why radius is the appropriate term, consider this, that here, if that's the radius, the interior of the circle is really all points that are a distance less than the radius from some center C, which I've put in here as a dot in the middle. Now, think about what this looks like. So this is 2D. Now think about what this looks like in 3 dimensions. If in 3 dimensions I draw sort of a globe like this, the interior of a sphere of radius r is all the points in 3 dimensions that are less than distance r from the center of the sphere. So this is the 3D case. Well, let's go backwards and ask what the 1D case looks like. You can see it a little bit by equations. This is going to be x squared plus y squared is less than r squared. That's the interior of a circle. For a sphere, we have x squared plus y squared plus z squared is less than r squared. That's the equation for, that's the inequality that gives the interior of a sphere. So let's take it back to 1D, where we only have one variable. That's going to be x squared is less than r squared. Well, if x squared is less than r squared, what that really means is just that the absolute value of x is less than r. So in other words, this is the center, and this is r, this is negative r, and this is r. So basically, the interior of an interval is really just sort of a circle or a sphere in one dimension. That's why the term radius is appropriate for what we're doing, because since the radius, the concept of any of these things, the sphere or the circle is always defined by a radius, where we say that we're interested in the points that are less than the distance radius from the center. That's what we're doing here in one dimension when we define an interval with a center of c. Okay, so that's a lot of words just to explain a concept that I know from experience that maybe about half of you find interesting. Okay, so the main substantive point about the fact that intervals of convergence are defined by a center and a radius is that these are impossible scenarios. In this case, what the green line represents what the interval of convergence is, and you see how it extends an equal distance from the center in either direction, regardless of whether the center is at an arbitrary c or if it's at 0. That makes these scenarios impossible. You can't have a situation where the interval of convergence for a series of center c is c minus 1 up to c plus 5. In other words, you can't have this situation for a center of 0. You can't have, if the center of the series, so if I have a series that looks like a0 x to the n, an x to the n, it's not possible for the interval of convergence of this series to look like this. It would be completely possible if, let's say the center was 2, because then I'd be extending 3 in that direction and 3 in this direction. So I'm not saying that negative 1 to 5 is an impossible interval of convergence for any power series, but it is an impossible interval if the center of the power series is 0, because the center of the series always has to appear at the dead center of the interval of convergence. That's one of the reasons that it's called the center. Okay. Now that we understand, hopefully, what the concept of a radius of convergence is, there are three types of radius of convergence are. One possibility is r equals 0. If this is the case, then what that means is that we have a series that looks like this. There's its center. It extends the interval of convergence doesn't extend any distance at all from the center, so the series converges only at its center, which I've written right there. The next possibility is that r is finite and positive. We don't have negative radii of convergence. If r is finite and positive, then what you have is the scenario that I drew above, where we have a series that converges for an interval that extends an equal distance in either direction from the center. The third possibility is that r equals infinity, in which case we just have, it doesn't matter where the center is, the series just converges every place for all real numbers x. So those are the three possibilities of the radius of convergence. I've written up here kind of a wordy process of determining where a power series converges, and like with anything else, it's going to make more sense once we actually do an example, but since I know some of you go back and watch the videos over and over again, and you should, because frankly, who wouldn't want to listen to what I have to say, I figured you can come back to this process if you want to see how to find the radius and interval of convergence. So the first thing you do is we use the ratio test. That's up here. So we use the ratio test, or the root test in some cases, but usually the ratio test, to find the radius of convergence r. And I will explain by example how to do that. But basically, most of these problems are going to start with the use of the ratio or root test. That will help you find r. Now, then of course, as I put in the chart, there you're really going to get three choices. You're going to get either r equals 0. Oops, there we go. You're going to get either r equals 0, r equals infinity, or r is a finite positive number. And as we talked about earlier, if r is 0, that means the series converges only at its center. note as an aside, it will converge at its center in all cases. If I say, if the question is, does this power series, converge nowhere? The answer to that is just false. There's no such thing as a power series that doesn't at least converge at its center. Um, Next, r equals infinity. That's, of course, the series that converges everywhere. The interval of convergence is then just negative infinity to infinity. If r is a finite positive number, then that means the series converges for that finite interval that I drew up here. In other words, this one. But there are still four possibilities, which are these. It means that we have one of these four intervals where the series converges. And as you can see, what the difference is this is the four possible combinations of the endpoints being included or not. In the first case, the interval includes both of its endpoints. In the second case, it includes only its left endpoint. The third case, only its right endpoint, and in the fourth case, neither endpoint. Half the work you do in determining what the interval of convergence is devoted to an analysis of the endpoints, because those have to be determined differently. That brings us to the second part of the problem, of the process, which is test both endpoints separately by doing the following. Substitute one of the endpoints of the interval for x in the series. So instead of having a series now in x, you're going to have a series that's just a number, just like an ordinary series like we did early on. Then you're going to use a test, and I cannot emphasize this enough, other than the ratio or root test to test those endpoints. As we will see, the endpoints are defined as the places where the ratio and root tests are inconclusive. So it makes no sense to apply the ratio and root test to the endpoints. You have to apply a different test. Once you know the endpoints, you've found the interval of convergence, and once you know what the endpoints are and whether the series converges or diverges at those endpoints, you found the interval of convergence. So I've put all this here. Let me just scroll through it. As we go through the process, if you want to sort of have these virtual living notes, you can come back to what I've written here and use that to just go through the recording and use that to go through the process.